All right, AP Chemistry, this is Mr. Robbins, and unfortunately, I am coming to you via video because I contracted COVID, which means I'll be gone the next 4 days from class, 4 more school days, and I'll be coming to you via video to help you out with certain content and to help you along. And I just have a couple announcements here, and then I'll get to some content. So if you can find your note guide that I gave you at the start of class last week, I'll work through the rest of that note guide today for you. And then for following days, I will post content videos on Google Classroom and I will let you watch them on your own using a Chromebook so that you can work through it at your own pace. And so you should probably bring a set of headphones to be able to work through those at your own pace. If you don't have headphones, I will get a set from the library so that you can listen to it in class at your own pace. Pause to write what you want to and things like that. Please email me with any questions you have the next 4 days. If you have content questions, that's great. I'll try to answer what I can over email. If I can't answer it, I'll make you a little video to help answer it. I don't want you to be lost in the dark. So don't get too stressed. If you have questions, just ask them and I'd be glad to help out. You guys have a Foundations practice quiz posted on Google Classroom. And this practice quiz you can take as many times as you want. It goes over things like significant figures, conversions, things like that, chemical change versus physical change, everything that you had to read in chapter 1. And you'll have a Foundations quiz on Friday. And you can take that in class. It won't take you the whole class period. Half of it will be multiple choice, half will be short answer with things like what you see today in our little presentation. If you have any questions on that, shoot me an email. I'd be glad to answer those questions. And we want to keep moving forward here so that we stay on track to have the right number of days for review before the AP test, which is why we're still going to have that quiz on Friday that we would have had if I was present with you guys. If that stresses you out, do not worry about that. Do the best you can on that quiz. And if you don't get what you want to, you can talk to me about it when I get back. So I want to give you the rest of your note guide. Hopefully you had a chance to get that out. The first part of that note guide has scientific notation in it. And scientific notation is a method for writing large and small numbers, both of which we find frequently in chemistry. Large numbers being counting atoms. We have tons of atoms in a sample that you can see with your eye. And small numbers being things like the size of an atom or an electron or a proton or a neutron. And so we run into large and small numbers frequently, and we want to write those the easiest way we can. And the way to do that is to write it in scientific notation. And to do that, you write your number as a number between 1 and 10, that's the first part, and you multiply it by 10 raised to a power. So here's the two that are on your note guide. This is a small number. It's the length of a base pair. If you remember in biology, a base pair is the distance across a DNA strand. A, T, C, G, you should remember those, hopefully. It's a really small number here. And here's what I want to do. I want to take my decimal, which is right here, and I want to move this to right here. If I move my decimal to right here, this number becomes 3.4. And 3.4 is a number between 1 and 10, which is the first part. So I'm going to write that. It's 3.4. And then I'm going to say times 10, multiplied by 10, raised to a power. And that power is going to be the number of decimal spots that I move here. And so I'm going to take my original decimal point. I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8 spots to get to my 3.4. So this is 10 raised to the 8th power. But I want a negative 8th power because we're a small number here. And the negative 8th power tells me to move my decimal to the left when I turn this back into standard notation. So this is scientific notation, and this is standard notation. Keep your units. We write our units at the end of our scientific notation like this, the meters. And I want to help you out. If you haven't seen this before in your math class, what does the negative power mean? Maybe you've seen this in your math class, x to the negative first power. We can write that as 1 over x to the positive first power. So I can do the same thing with my 10. 10 to the negative 8th power is the same as 1 over 10 to the positive 8th power. Well, that's the same as 1 over 10 times 10 times 10. I won't write them all out here, but 8 of those. 10 times 10 times 10, 8 times. So that's just saying divide by 10 8 times. That's what the negative 8 power means. If I divide by 10 once, 3.4 divided by 10 becomes 0.34. Divide by 10 again, it comes 0.034. If I do that 8 times, we get our number back up here. That's why it's the negative 8 power. For our positive ones, that's for large numbers. The number of base pairs in a human cell is 6 billion base pairs. And if I want to make this scientific notation, there's an implied decimal right here at the end of my number. I want to move that decimal all the way to here, and it makes my number 6. You can write 6.0. I'll just write 6 right now. You'll see why after we talk about significant figures. But I'm going to say 6 times 10 raised to the power of, and I need to go back to my number. I'm going to move my decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9 spots. So this is 6 times 10 raised to the positive 9th power. Include your units base pairs. Okay, you can do that for these two, writing in standard notation. They're given to you in scientific notation. I'll do that right away up here on the board. And our first one here is going to be a bigger number. 10 to the 24th is a positive power. And so I'm going to take my decimal here. I'm going to move it this direction 24 times. And the 9, the 7, 2, 1, 9, all of those count as spots that I'm moving the decimal. And so this would be my first spot. So that's 1, 2, 3, 4, 5. 5 spots to get to the end of my number right here. I'm going to keep going because I have to go 24 times. So that's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And that is a lot of zeros. That's the mass of the Earth. Put your units at the end in kilograms. And that's written in standard notation. Now you can see why we use scientific notation in science. If you had to do math with this and report it to someone, writing all those zeros multiple times, there's going to be a great possibility of having an error with the number of zeros that you write. But if I just write 24 up here, I can repeat that many times on the same page without making a mistake. My negative fifth here for the width of a human hair, that means it's a small number. So I'm going to start out with my decimal here. I'm going to move it this direction, 5 spots. So this would be my decimal point, 1, 2, 3, 4, and the 5th spot is the 1 here. And I'll include a 0 after it, and you'll see why after we talk about significant figures. And this is going to be meters, and this is our correct answer. If you want to check it, I can write this in scientific notation again by moving my decimal to right here. That's my 1.0, and let's just count our spots. 1, 2, 3, 4, 5 spots. That's what I have, so I have the correct answer there. A little side note about your TI Nspire calculators. When you're writing scientific notation in a calculator, you want to make sure that you type it in like this. Let's just say I want to do 5.6 times 10 raised to the 5th power. I'm going to write that out. Instead of writing it like this, I'll show you the way I recommend not doing it first. I can write times 10 and then use the little caret key here to raise it to the power of 5. And if I hit enter here, you're going to see, oh, I didn't get it big enough. Let me do 5.6 times 10 raised to the, let's do to the 9th power. And if I hit enter here, you're going to see the calculator automatically converted this into what calculators like to use for scientific notation. This capital E means times 10 raised to the power of, and then the number after it is what we raise our 10 to the power of. And so these two mean the same thing in the calculator. The difference is for the calculator on the left side here, this is two different numbers for the calculator. The 5.6 is separated from the 10 to the 9th power. And over here, the calculator treats this as one number stuck together. And so I strongly recommend you type it in like this, 5.6 e to 9th. So when you're doing math, it doesn't accidentally take order of operation into account and separate these two numbers, thereby calculating your answer incorrectly. And that usually happens when you're doing division. And so if I want to type this in, I'm going to show you how to do this, 5.6. Instead of writing times 10, I'm just going to go down here to the A. Just to the left of the A is the EE. They're both capitals. And if I hit that, I get that capital E. That means times 10 raised to the power of. And now I can put my 9. And now I can do my math with it. If you want to do division in your calculator and do it a really fancy way, which is the way I like to do it in these calculators, if you hit Control and then divide, it'll give you a fraction so you can make sure what's on top stays on top and what's on bottom stays on bottom. And then you won't have those problems with things moving around. Okay, so there's your little side note for your calculators. I hope that helps. We'll keep going with your note guide here. For measurement, we already talked about this, how you measure. And so I won't go over this again. But we didn't get the chance to write down these two things in your notes. You can pause the video if you need to here. But accuracy is the closeness of a single measurement to its true value. So when we're measuring things, if you have a good device, so they manufactured the device well, like a graduated cylinder that has marks in the right spot or a ruler that has marks in the correct spot, that means that device will be accurate. It's going to be good at measuring the true value for that length or volume or whatever the device is made to measure. Precision is something different. Precision is using the same device multiple times. So you can read your definition here, but think about this. If I gave you a ruler and I said measure the distance across your piece of paper 10 times with the ruler, and the 10 times you measure 11.5 inches, and then you measure 11.7 inches, and then you measure 11.4 inches. This would be a device that has pretty poor precision. These numbers from the same device, identical measurements of a quantity obtained from the same device, are pretty far apart. So that device can't repeat its measurement very well. Devices that have high precision, if you take multiple measurements, you might get something like this: 11.56 on the first one, and then 11.57 and 11.55. And these measurements are really close to each other. They're all within 0.01 inches from our middle number, 11.56. This is a high precision device, and this would be a low precision device. And so that's what that little definition means. And significant figures. Why does this matter? When we're doing math with numbers, and numbers is what we base a lot of chemistry on, and physics and other sciences, we want to make sure that we're doing the correct math to come up to the correct conclusions. And you can think about when we did our first little activity with the napkin and the paper towel, and I asked you to use your device to the correct number of precision digits. So when you're measuring your measurement, you had to make sure you measured this correctly with your device, the marks on your device. Only from those measurements can you make the final judgment call that the paper towel is more absorbent than the napkin. If you had a really poor device, you couldn't make that judgment call. And in chemistry, it's the same thing. When we make theoretical arguments about what happens in an atom, we're making those arguments oftentimes based on numbers. And those numbers have a certain amount of precision that goes with them. And that's what significant figures are. It's a way to keep track of that precision. And significant figures are all certain digits plus one estimated digit. And let me go back to our measurement here. If you remember when we did this on the first day or second day, when we measured this, we said that we were certain that this block was greater than this mark and less than this mark. And because of that, we could say 1.3 with certainty. And then we estimated that it was like 1.36 or somewhere in there. Centimeters is what we called this. And maybe someone estimated 1.37, but these first two digits were the exact same for everyone measuring with this device. These are the certain digits, and this is our one estimated digit. And so all of those digits, all the certain digits plus one estimated digit, count as figures that are significant for a measurement. And we have some rules. If we didn't measure it, we don't know. And so they have a set of rules to keep track of these. And these should make sense to you if you think about measuring. Here's your rules. It's on your little printout. All non-zero digits are significant. So if you have a number like this, 126, all three of those count, and this would have three significant figures. I'm going to abbreviate sig figs. You're going to see that a lot throughout this course, or just SF. This has three significant figures. All final zeros after a decimal point are significant. This is key that it's after a decimal point. So this would be a number like this, 15.0. The 1 and the 5 apply to rule number 1. They're all non-zero digits, so those count. And then this 0 is after a decimal point, so it counts as well. So this would also have three significant figures. All of those figures count. If I did something like this, what if I did 15.00? All of those zeros count because they're after a decimal point. What if I did something like this, 15.100? Well, all those zeros count, and so does the 1, because rule number 1 says all digits that are not zeros count. So this would have 4 significant figures, and this would have 5 significant figures. Rule number 3, zeros located between significant figures are significant. So zeros located between significant figures would be something like this, 105, because this is sandwiched between the 1 and the 5, which rule number 1 says those are significant digits because they're non-zero. This 0 automatically counts. It's stuck between the two, so this would also have 3 significant figures. I'm not trying to make all of them have 3 significant figures. It's just happened to work out that way. But the 0 sandwiched between counts. And that works if there's multiple zeros. So something like this would also, all those zeros would count. This would have 4 significant figures. It could be after the decimal as well. And number 4, zeros used solely for spacing the decimal, this could be in front or behind it, are not significant. I want to show you, there's kind of 2 examples for this that you want to have down. The first example is spacing the decimal for a large number. So if I write something like 1200, this is spacing the decimal. It's implied that the decimal is right here. We don't write it, but these zeros right here are spacing that decimal just to write 1200. That's the only way to write it. And so we don't count these because we don't know if the person who measured this had marks every 1,000 and estimated to this spot, had marks every 100 and estimated this spot. There's no way to know from this written value. And so they just say, let's err on the side of less precision. We're not going to count these zeros at all. So this would only have 2 significant figures. If you wanted this to have more significant figures, you would have to write this in scientific notation. I can write this as 1.200 times 10 raised to the power of, my decimal starts here, move it to the left, 1, 2, 3, 10 to the third power. And now this has 4 significant figures because I have 2 numbers that are non-zero, that's rule number 1, and I have zeros that follow the decimal, and this is after the decimal point in scientific notation, it still counts, and those count as significant digits. So this would have 4 now. So that's your first case, spacing the decimal for a large number. These do not count when you space the decimal for a large number. For small numbers, if I want to write something like this, 0.00036, these space the decimal to make the number small. They do not count either. So these guys don't count. This would only have 2 significant figures again. We don't get to count the zeros in front of this. But if I add a 1 in front of this, like this, now all those zeros count because they're sandwiched, and this would have 1, 2, 3, 4, 5, 6 significant figures. So those are your rules. I hope that makes sense to you. We're going to use these rules to keep track of precision when we do math. I want to give you a little kind of disclaimer. We are not going to spend the rest of the year just being nitpicky with these. There are rules that we're going to learn right now for this unit. We'll apply them generally, and I'll talk to you how we apply them generally the rest of the year. And right before the AP test, I'll show you how to find the 1 point on the AP test. It's only 1 point every year that has to do with significant figures. So right now, just try to learn them, get them down, but don't worry that we have to think about this all year, okay? So on your sheet, you have these guys. Go ahead and pause the video if you can here to work through these and see if you can write down how many significant figures each of these numbers has. Okay, hopefully for A, you got this. This only has 1 significant figure. I'll abbreviate SF. These zeros do not count. They're spacing the decimal. B, these zeros also do not count. They're spacing the implied decimal right here for 100. So this also only has 1 significant figure. For C, this zero doesn't count. It's just spacing decimal, just holding a spot there. This does because it's non-zero. And these count because they're after a decimal and they're trailing zeros. So they're after decimal and they're after a number. That's different than these zeros out here. These are after decimal, but they're not trailing at the end of the number. The number doesn't start till it's 2 here. So these zeros do count at the end, but these ones in front do not count. Hopefully you did not count those ones for this part E. So these have 3 significant figures. This would have 2 significant figures. This zero doesn't count. It's spacing the decimal. These 2 count because they're non-zero. These guys do not count. They're spacing decimal. This 2 counts, and this is a trailing zero. It's at the end after decimal, and it counts. Any zeros after a decimal at the end of a number count. So this would be 2 significant figures. This would have 1, 2, 3 sandwiched between. The 0 counts. This is after a decimal, and this is at the end of the number. It's not just spacing a decimal like this. So these zeros count. It's after a decimal, and it's at the end of a number. So this would have 5 significant figures. And this guy right here would have 2 significant figures. You don't count anything with scientific notation here. Just look at the decimal. And this would have 4 significant figures. Again, don't count your scientific notation. Just look at your number with decimal. Okay. Exact numbers. These are numbers that are not measurements, and these numbers are not considered when keeping track of significant figures. So these would be numbers like counting numbers. If you count how many students are in the room, and we count 26, for your guys' class it'd be 12. We are exactly 26 students or 12 students. And I could write that like this, 26.0000, and keep going forever. But it's an exact number. And because of that, this has infinite precision, and we don't worry about it when we're doing math with numbers. They're exact numbers. This is not going to limit the precision of any calculations because it's exact. Exact conversions are treated that way. They're exactly 4 quarters in $1. Nothing more than 4 quarters and nothing less than. And we just write 4 and 1, but we mean exactly 4 and exactly $1. And so that has infinite precision with it. It's infinitely precise. So when we're doing math with these numbers, we have a couple rules. We want to keep our precision throughout our problem. So if you measure two things and you want to add them together, the thing that has the least amount of precision is going to dictate what your answer can be with the amount of precision that we report. So for both of these, addition, subtraction, and multiplication, do the calculation first. So we can add this together. 18.1 plus 2.06, hopefully you can do that in your head, is 20.16. I do the math. And then if it's addition or subtraction, round to the least number of decimal points. The least number of decimal points in my numbers, I go back to the numbers I started with. Right now we only have 2, but you could have like 5 here. You look at every one of them. And here I have 2 decimal points. And here I only have 1 decimal point. So the least number of decimal points would be from this number. It's limiting my precision. And I'm going to round my answer to the least number of decimals, which is 1. So this would be rounded to 20.2. And that's my final answer. Okay, that's addition or subtraction. Multiplication and division, same thing. Perform the calculation, and I'm going to plug this into my calculator. If you multiply those two together, you get 22.886, and this becomes meters squared. A meter times a meter is a meter squared. And I'm going to round this. The answer gets the same number of sig figs as the original value with the least number of sig figs. So now I'm going to go back to my numbers, and I want to count my significant figures here. And again, this could be 5 numbers. Right now we only have 2 numbers multiplied, but you do this for every single number. We want to find the one that has the least number of significant figures. So this has 1, 2, 3, they're all non-zero, 3 sig figs. This has 1, 2, 3, 4, 5 sig figs. And it says I want to report my answer with the least number of sig figs in my original numbers. Well, that's 3 sig figs. So this needs to be rounded to 3 sig figs. How do I do that? Start on the left. We want this one. We want this one. We want to round to this spot. That has to be our last number. So after the 8 here is another 8. That means I round up. This becomes 22.9 meters squared. And now I have 3 significant figures in my final answer, which is the same as the least number that I started with. And that's how I keep track of precision with multiplication and division. Okay, see if you can do the following problems. You can pause the video again, and I'll give you the answers here in a second. Okay, here's your answers if you just plug them into the calculator. Now we have to round them correctly with our rules. If you add, you want to do least number of decimal points. This one has 3 decimals, this one has 2, so our answer should have 2. I'm just going to take and keep the 2 and the 3. So this would be 7.23. Make sure you keep your units. If you add inches, you get inches again. Subtraction, least number of decimals. 1, 2 decimals, 2 decimals, so my answer gets 2 decimals. I don't have to do anything to this. I just need units. I'm multiplying, do the math, and then least number of significant figures. This has 3 significant figures. This has 4 significant figures. The 0 counts that's sandwiched in between. So my answer should have 3 significant figures. 1, 2, 3. Round to the 7 spot. There's a 9 after it. So this becomes 8.8. 94.8. A meter times a meter, again, is a meter squared. Okay, our last one, 3 pencils times my length of the pencil. This is an exact number. It's a counting number, so I do not count this when I'm trying to keep track of precision. It's exact. So that means the only thing I have to go off of is this one. Multiplication tells us to do the least number of significant figures. This has 3 significant figures, so my answer should have 3. 1, 2, 3, round to the 7 spot. It's a 4 after that, so it rounds down. And we keep 19.7, and this would be centimeters. I hope that helps for your significant figures. I'm going to stop the video here. I know it's not the rest of your note guide. You have conversions and metric on your note guide. I'll make another video so that you're not sitting watching a video the whole time here to walk you through metric conversions and how to do dimensional analysis. If you remember that from general chemistry, you don't need to watch that video. Just work through those practice problems on your note guide. If you don't remember that, look for that video posted on Google Classroom. Again, just a reminder, please email me if you have any questions. I'd be glad to help out.